Hello, Algebra 2. In this video, we're going to talk about the imaginary number I, and we will start off with the definition. I has been defined as the square root of -1, and I squared is equal to -1. Those two are both parts of the definition. And if r is a positive real number, then the square root of -r is I root r. So, the square root of -8 can be simplified to I root 8, and then of course that just takes care of the negative under the radical and shows us that we have an imaginary number. But to take this a little bit further, we know that 8 is 2 root 2, so I'm going to write that as 2I root 2, and that is the simplified version of the square root of -8. Now, the square root of -8 is an example of something that we call a pure imaginary number. So a pure imaginary number is any number in the form bi, where b is an element of the real numbers and b is not equal to 0. So real number times I, pure imaginary. So I can take purely imaginary numbers and then perform operations on them. So for example, if I see the square root of -81 plus the square root of -36, I am going to convert those into imaginary format with an I. So the square root of -81 is I root 81, and the square root of -36 is I root 36. And of course we know root 81 is 9, so this is 9I, and this square root of 36 is 6, so this is 6I, which gives us a total of 15I. So when we are asked to work with these numbers, you want to convert them so that they have the I for imaginary, and you treat those I's just like you would variables and combine like terms as necessary. So now we're going to talk about multiplying pure imaginary numbers. And so if I have the square root of -9 and the square root of -16, I have to first convert them into I format. So I root 9 times I root 16, which gives us 3I times 4I, because root 9 is 3 and root 16 is 4, and then I multiply 3 times 4 and get 12, and then I get an I times an I, which is I squared. And remember, the definition said I squared was -1, so this is 12 times -1, or -12. Now, this is what you're supposed to do, but you have been used to working with radicals and a particular rule of radicals that says you can just multiply these two together. So you would have like -9 times -16, and then this would simplify to a positive 144 and give you a 12. Well, this is not correct, because that property you learned in the real numbers does not hold in the complex or imaginary numbers. You remember the rule, the root a times root b is equal to root ab, and we would use it both directions to simplify radicals. Well, this is not true when both a and b are negative. So when you have two imaginary numbers multiplied together, this property does not hold. So you have to remember, when you multiply imaginary numbers, they have to be in that form with the i's first. So if you're asked to simplify something like 3 over 4I, you might be thinking, well, that's fine. But you have to remember that I is a radical, and we cannot have radicals in the denominator. So we have to multiply the numerator and denominator by 4I. We get a 12I in the numerator. In the denominator, we get 16I squareds. And you want to just cancel off those i's, but you do not do that, because remember, I squared is -1. So we have 12I over -16. And we don't like 12 over -16. We can divide both those by 4. And we get 3I, -3I over 4. So now that we've seen a little bit of the imaginary numbers in action, we can define our new number system, which is the complex number system. So the complex number system has some subsets that we need to make clear. First, there is a subset of numbers called the pure imaginary numbers, meaning they only have an imaginary component, that bi, where b is not equal to 0. Then we have numbers that are called imaginary numbers, and imaginary numbers have both a real and an imaginary component. So they're not purely imaginary because they have that real component, and of course you're going to be imaginary when b is not equal to 0. And the complex numbers themselves include the set of all of the real numbers plus all of these imaginary numbers. And if you think about this set of imaginary numbers, within this set live the pure imaginary. So if I were to draw a Venn diagram of the number system, this rectangle would represent the complex numbers, right? And inside the complex numbers is a partition. These are the numbers that are only real, and these are the numbers that are imaginary. And inside the imaginary numbers live the purely imaginary numbers. Over on the outside of the purely imaginary are these numbers that have imaginary and real components. By definition, a complex number is any number in the form a plus bi, where a and b are real numbers. And it is a real number when this b is 0. So that's real number. Pure imaginary, imaginary, all of those numbers, and any number in this form is a complex number. A is called the real part because, well, it's real. And b, not bi, but b is the imaginary part because that's a component that gives us the imaginary number. Now, there are some basic properties of the complex number system. First, in order for complex numbers to be equal, if I have a situation where a plus bi equals c plus di, that's only true if and only if a equals c, meaning real part equals real part, and b equals d, meaning imaginary part equals imaginary part. And the sum's quite simple. It's like combining like terms, right? You add the real parts, a and c, and then you add the imaginary parts, b and d, and you put the I on there. Now the product's a little bit different. You can, of course, memorize the product, or you can just realize, you know what, these two things are binomials, and I can just multiply them together. All right, so let's derive what the product of two imaginary numbers are using the distributive property. So I have a times c, and then ADI, and then I get BCI, and then BDI squared. So then I'm going to simplify this part here. So I have AC plus ADI plus BCI minus BD. And why is it minus BD? Well, because I squared is -1, and so it means I just changed the sign. So now what I'm going to do is I'm going to gather the real parts. So I have AC minus BD. That's the real part of the product. And then gather the imaginary parts by factoring out the I. And I get AD plus BCI. So by definition, the product of two complex numbers, a plus bi times c plus di, is actually this thing here. And remember that for proof, if you have to prove, say, that multiplication commutes in the complex number system, you use this as your definition of complex multiplication, and you don't have to show those two steps up there. Now, one important thing that we have to talk about when it comes to complex numbers and, well, numbers in general, are these things called conjugates, okay? And in Algebra 2, we look at conjugates as being binomials with radicals whose products are integers, and they're used to rationalize denominators. So 8 minus the square root of 7 and 8 plus the square root of 7 are conjugates, because when you multiply the two of those together, you're going to get an integer. And we like to use these when I say I have to simplify something like that. 2 over 1 plus the square root of 2. I can't just multiply it by root 2 over root 2 to rationalize a denominator. So what I have to do instead is multiply by the conjugate, and the conjugates rely on the concept of difference of squares. That a squared minus b squared, remember that factored to a plus b times a minus b? So if I look at this, this is like a plus b, that's like a minus b. So when I multiply them together, I get 1 minus root 2 times root 2, which is 2, over 2 minus 2 root 2, which is just, that's negative 1. So it's negative 2 plus 2 root 2. And that's how I would rationalize that denominator. Okay, and I can do that because 1 plus root 2 and 1 minus root 2, or this a plus b, a minus b, are called conjugates. Now, I bring that up now because, of course, complex numbers have conjugates. And there are quite a few properties that deal with complex numbers and their conjugates, which is what the second complex number video is going to be about that you'll watch later. So a plus bi and a minus bi, these are the two conjugates. And when I multiply them together, I get a real number. That's the special thing about complex conjugates, is when I multiply them together, the imaginary parts go away and I'm left with a real number. And simply speaking, once again, it goes back to that difference of squares thing. A plus bi times a minus bi is going to be a squared plus b squared. And you're thinking, oh, wait a minute. It's supposed to be a squared minus b squared. But when you actually do the multiplication here, bi squared, remember, is going to be squared I squared, which is negative b squared. So negative b squared is going to make that positive. So when you multiply two conjugates together, complex conjugates, you get a squared plus b squared. And the whole point of complex conjugates is to be able to simplify when I have an I in the denominator. Because remember, I is the square root of negative 1, and I cannot have radicals in the denominator. So if I ask, hey, what's the reciprocal of 5 minus 3i? You can say it's that, which is true, 1 over 5 minus 3i. However, that is not simplified. So what I have to do is I have to multiply top and bottom of my fraction by the complex conjugate, and I get a 5 plus 3i on top. And remember, when I have a plus bi and a minus bi, that simplifies to a squared plus b squared. So a in this case is 5, so it's 25 plus 9. So that means that the reciprocal of 5 minus 3i is 5 plus 3i over 34. Finally, we're going to end this video with a couple of properties that hold in the complex numbers. Basically, all the field axioms that you know with addition and multiplication in the real numbers still hold in the complex numbers. They're inverses, they're identities, they're closed, they have associative, commutative, and distributive properties, and you're actually going to prove many of those in the coming days. The properties of equality still hold: reflexive, symmetric, transitive, addition, and multiplication. However, one very important thing, there are no properties of order, meaning you are not going to see inequalities with the complex numbers, primarily because you cannot put the order imaginary numbers on a number line. So in order for you to have order, you have to show something is greater than something else on a number line. And since imaginary numbers cannot be plotted on a number line, they have no order. You cannot say that one imaginary number is greater than another imaginary number. As a matter of fact, when you plot imaginary numbers, they're not on a number line. You actually plot them on a plane where one axis represents the real part and the other axis represents the imaginary part. So your numbers end up being dots in a coordinate plane. So there's no saying one of those dots is greater than another dot. So no properties of order in complex numbers.